So starting off, I know that we spent a lot of time last year. You memorized the SI units, several of them, a lot of prefixes. That just holds true over into what we do for physics. Never ever will these units and prefix systems for the SI system go away. So we will talk about the ones that you need to know. So keep that in mind. We talked about what a single dimension is versus a derived unit. It gives you examples of single dimensions. We'll get to the specific ones that you need to know, and we'll add on to those as we go throughout the year. This one right here, derived units, things like speed, velocity, density that we covered last year, wherever you have to start combining units, those are going to be derived units. And then, again, this just gives you some examples. Now we're getting into the prefixes that I do expect you to know. On these right here, it's not all of these, but the ones that I am wanting you to look at are going to be nano there, all the way through mega. So start with mega, which is 10 to the 6th, then work your way all the way down to pico, which is 10 to the negative 12th. So with the dimensions and units, when we talk about dimensions, we're going to have a video right after this. It just gives you what a definition of a dimension is, and that you've got to have correct dimensions whenever you go to either do a calculation or if you're collecting data, which we'll start collecting data in a lab tomorrow. You have to have correct units. You know, if somebody wants you to work in centimeters and you're working in meters, that can throw your data off. If somebody wants a velocity but you give them acceleration, the units are different, therefore it can throw your data off, and then furthermore your calculations. So again, don't worry too much on this part right here, but we'll get to a video just to help explain this.
Buying new carpet for a room. You need to tell the flooring company how much material you will need. The answer can be found by measuring the length and width of the room and then multiplying the two measurements to find the area. If the woman on the left measures her distance in centimeters and the woman on the right measures in meters, we have a problem. The units do not make sense because they do not represent the area the carpet must cover. If both women measure in meters, the answer is much more useful. Now you know how much carpet you will need.
We're going to go through a sample problem. I'm not going to go through exactly what they do on the PowerPoint, because obviously y'all know when we do conversions, I do mine a little differently than what any of these PowerPoints or what Holt does. And we will go back and we'll use the grid system. Hopefully y'all remember that. We'll go through, again, the steps to that, but we'll see. And this one right here, it's talking about you've got a bacterium with a mass of about 2 Fg. What is Fg? Okay, what does it stand for? I told you that would be later on the PowerPoint, but it's femtograms. So we're going to go from 2 femtograms, and the first one we're going to do is go to grams. So if I'm looking at this, again, if I need to write these steps down, let me know, but hopefully just verbally you'll catch on pretty quick, or remember pretty quick. What unit has to go here at the bottom? The femtograms. Okay? What unit's going to go at the top? Grams. And since this is straight SI to SI converting, you can do this in one step. The next thing you've got to keep in mind is the 1 goes with your larger unit. Which one's larger? Gram. And then a 1 with so many zeros goes with femtograms. And what did we say is the difference between exponents of femto and then our base gram? Negative 15. But do we put a negative 15 here? It's actually a positive 15. So if you put a 1 with the larger unit here, then a number greater than 1 has to go with your other unit. So that's why you go with the positive 15. The difference in exponents between 0 and negative 15 is 15. That's why it's a positive number there. Or not a positive number, but a number greater than 1. Yeah.
Are you still going to make us show those steps?
No. The grid? Okay. As far as the grid right here, starting off on our first test, yeah, you will have grid work to do. But then later on, you know, when we get into much more complicated stuff, this will be the easy stuff, and you're doing it in your head. Okay? Right. Right. But like I said, for the first chapter, you will be showing the grid. We'll have practice work later. And then on your test Friday. But yeah, you'll have to show the grid. Now, if significant figures are part of this PowerPoint, but we are not working with significant figures. But be reasonable. I mean, you did learn the rules last year as far as rounding rules, significant figure rules. So just be reasonable whenever you're doing your calculations. Now, when I do this calculation, you get to use your scientific calculator. So when I do this, my answer is going to be 2 times 10. What's my exponent going to be in my answer? What? Negative 15. 2 times 10 to the negative 15 grams. That 15 is in the denominator. And your rules were for scientific notation. If you're dividing, which we are here, you take your exponent in the numerator, subtract it from your exponent in the denominator. So in this case, it's really 0 minus 15. You get a negative 15. But you have your scientific calculators. That should do those steps for you without you having to remember them. Now the next part is dealing with kilograms. So on your paper, I want you to write out what that should be here. So again, on this one right here, it shows you the grid, shows you how we get different parts. Since it's SI to SI, you can do the grid in one step. You're going to have to be really careful on your test. The test in physics from day 1 all the way through to the very end, they will constantly test you on, do you recognize the units that are given and can you use them appropriately? Because units might be given one way in the question, and then if it's multiple choice in the answer, they give you a totally different set of units. And if you don't notice that, it's not that the problem might even be hard, but if you just don't notice the little difference in units that they like to do constantly, it's real easy to miss a problem. So I just skipped over everything dealing with accuracy, precision, rounding rules, significant figures. All of that was at the end of Section 2. And in this chapter, if you notice, we never covered anything in Section 1, so that won't be on your test. Now we're into Section 3. Again, you're not going to learn anything new here in Section 3. It might be presented a little bit differently. But everything that we have just talked about as far as conversions, and then what we're going to talk about here in Section 3 will play a heavy role in what we do in our lab. You're going to collect a lot of your own data. Once you get your computers, whenever that is, you're going to plot this data. You're going to make some tables and some graphs from the data, answer some questions. But that's what we're going to do. So this just goes into what are tables, what are graphs, what can you do with equations. And then we're going to look at a specific experiment from Galileo, and it'll go through what it does. So in this data right here, and you don't have to write down any of this data, it's more important that you understand what they're going to do with it. But over a certain time frame, they look at the distance a golf ball falls versus the distance a table tennis ball falls. And can you see anything special about those distances? They're essentially the same. Do you remember on the previous slide what it said? These balls are actually dropped in what? In a vacuum. They're dropped in a vacuum. So here is the data that is plotted. Would you consider this to be linear data? What does it mean to be linear whenever you plot data? It's a straight line. And that is definitely not a straight line. And you're going to have all kinds of data this year. If we were doing density data, it should give you a straight line. We had that last year. A lot of what we do, especially dealing with velocity and acceleration, stuff like that. We'll go through tons of scenarios where sometimes it's constant, sometimes it's linear, sometimes it's exponential, and we'll get different types of plots, and we'll look at those today.
Can tell you about the relationship between sets of data. This graph shows a linear relationship. As the mass increases, the volume increases. This graph is similar to the linear graph, except that it is not a straight line. It curves, becoming increasingly steep. This curve is characteristic of an equation in which one of the values is squared or raised to some power.
So on the previous one that we looked at, where mass and volume were linear, it was mass divided by volume, which was for density. In this one, it's a little bit different. You've actually got volume is squared instead of just volume to the first power, so that's why the data is going to look a little bit different.
This graph has a steep curve that approaches but does not touch the axis. This curve is characteristic of an inverse square. As one value increases, the other becomes smaller.
So they gave you a few different types of graphs. What kind of graph is this one called? Inverse square. This slide is not too important in the fact that it's talking about if you were using the textbook, what would be boldface, what would be italicized. Even in here, variables can be boldface or italicized. Units, a lot of our units are going to be traditional letters, and then you'll be introduced to a lot of Roman letters as well. Dimensional analysis, order of magnitude estimates, that's just talking about a couple of tools that we're going to use. Right here they're giving you specific information as far as that drop ball experiment worked with Galileo. They give you words that are here in and then they turn around and give you symbols to tell you, well, what does change in position mean? So whenever you see the letter Y is going to have something to do with change in position. And typically Y, if you're looking at an XY axis, which axis is the Y, the horizontal or vertical? It's the vertical axis. So if you see delta Y, it's talking about a change in vertical position. So anytime the rest of this school year, when you see delta Y, it's going to have something to do with change in vertical position.
Y or delta Y?
Delta means a change in. If we look at a change in for delta, what does that typically mean? How do you define it? Whether it's a change in temperature, a change in time, a delta can be used for endless variables. Change in temperature, change in time, change in speed, change in acceleration. It is final minus initial. So anytime you see delta, you take the final minus the initial, whatever variable you're looking at, that's what it's going to be for. And then again, lower t right there for the rest of the year is change in time. So anytime you see that lower italicized t, it's talking about time.
What is Y?
Y, that's your change in vertical position.
Analysis and estimation help you to check the accuracy of your calculations. Suppose we are about to take a trip to a city 725 kilometers away. We expect our average speed to be 88 kilometers per hour. How long will the trip take? We first verify that we have set up the equation correctly by making sure the dimensions of the answer are what we expect. Only one combination of speed and distance will have the proper dimensions to give us the time.
Have you already figured out what it is? Do y'all know what the formula for speed is? Okay. Without having to go through all of this for whatever reason, it's stopped kind of right in the middle. Several of you have already said what it is. So if we've got speed, and later on you're going to learn that we're going to use V for velocity, even for speed, and we'll talk about the difference, is distance divided by time. Plug in these different calculations. We're trying to solve for time. If I rearrange this equation to get time all by itself, what happens to your V and your D? If I want to get time all by itself, what happens to V and D?
V is under D.
Okay? That's it. Now I'm going to just plug in units. Distance, the unit over here is km. What does km stand for? Kilometers. And for velocity, it's km over h, which is kilometers per hour. I typically use HR for hour. You notice anything special that happens to those units? Km cancels out. And then you're left with 1 over hour. So hour actually ends up being back in the numerator. So you've got 1 over hour. Instead of dividing that, if I wanted to multiply it, 1 times, what do I do to this? Instead of dividing, I multiply. What do I have to do with that part? In math class, what do you do? If you change your mathematical operation from divide to multiply, what do? You flip it. So that ends up being hour over 1. And you can tell right there you're left with hours. Is hour an appropriate unit for time? It is. And they would have went through several scenarios, given, they would have arranged it different ways, but to keep in mind the rest of the year, whenever you finally get an answer, keep your units attached as you go. And if your units don't make sense for your final answer, you probably got something switched around early on.